So I start off with where I'm coming from, which is Norbert Wiener's definition plus a couple of bits. So I've always been thinking of some sort of jazzy slogan. If it moves, it's mechanical engineering type slogan, and this is my first attempt. I'm sure you can think of something better. Please let me know if you can. So again, for people who think it's something to do with cyborgs and Star Trek and that sort of thing, it's a bit more than that. And these are sort of examples which many people would agree, I think, are examples of cybernetic systems, if not practically everything in the universe. These, I think, are some of the milestones. I'm an electronics engineer, a physicist, so I come from a different perspective than most people. I think the telephone patented is important because that's the forerunner of the internet, of course. The electronic amplifier is a major part of civilization. It's one of the major developments of civilization because it has enabled telecommunications, the telephone system, radio, TV, everything depends on the amplifier. Interestingly, we had the movies before we had silent movies, before we had sound movies, because amplifiers didn't exist in the days when they were making films. It wasn't until the amplifier was invented we could have talking pictures. An important aspect of how amplifiers work was the discovery and the mathematical work on negative feedback. This was very important because amplifiers are made out of valves or transistors, which are very poor devices, and you can make an amplifier which is essentially perfect out of components which are essentially poor. And a negative feedback enables you to make essentially a perfect item out of something which is essentially components which are poor. It's completely opposite to the concept of a chain is only stronger than the weakest link. You can actually make strong things out of weak things using negative feedback and amplifiers. First electronic digital programmer, a digital computer, Colossus, the machine that was used to decode the Enigma machines during the war. Then the invention of the transistor, very important, which changed those huge great valves into something very tiny. The operational amplifier is important. Many people may not have heard of it unless you're an electronics engineer. This is an amplifier that was designed to do mathematical operations for the early analog computers and turned out to be very much more useful than just that. And virtually every student of electronics will use almost nothing else but operational amplifiers. Andrew mentions Gray Walters' tortoise, an initial first step. Very interesting because it could be described as the first example of artificial life. Manchester Baby, first door program computer. You would guess, if there are any Americans in the audience, apologies for this, because Britain did have some sort of contribution to cybernetics computing. If you just read Wikipedia, I might get a different opinion. Transistor radio important, and then when they are able to get transistors all on one chip, to get now millions and millions of transistors on one tiny little chip the size of a thumbnail, a sort of magical achievement. And then in '81, the first laptop battery came out, which enables advanced robotics, portable computing. And then, of course, 1991, the birth of the World Wide Web, which is a major interest to cyberneticians. I mentioned the negative feedback amplifier. So the A is the amplifier, and the concept is you take a little bit of sample of the output, feed it back to the input, invert what you've feed back, and it can make essentially a very faulty amplifier into an almost perfect amplifier by feeding the errors back and having the amplifier correct its own errors live in real time, which is kind of magical in many ways. This rather interests me because the first time I got used to making oscillators, and then one student came to me one day and said, well, how does an oscillator work? There's no input. How do you get an output? And how come the output is perfect? There's no distortion. It's exactly the right amplitude. It's exactly the frequency. You say, how can that be possible without an input? It's a bit like the birth of the universe or something. Where did it all come from? And all you need is an operational amplifier which has two inputs. One amplifies the input, and the other one inverts the input and then amplifies it, and you can get perfect sine waves just out of a simple circuit like that. And the filter and the gain control. The gain, interestingly, is again, controls itself. So it's a self-controlling circuit, which is rather interesting in my humble opinion. Something a bit more complicated, which is an engineer's block diagram idea of what a human being is. We have sensors, actuators, and a brain, and there's lots of other stuff in between, of course, that makes it all the rest possible. But the main thing is we have 5 sensors. We have some internal sensors, 5 external sensors, some internal sensors. Our brain, of course, has evolved over the years from a very, very simple animal brain, reptile brain that just does the simple stuff, and then as the brain has evolved over billions of years, it's become more complex and added layers have been added to it. So you can now capable, after billions of years of evolution, abstract thought, language, and self-control. The only output we have is muscles, and an important aspect is feedback. It's a bit slow for humans. About 100 meters a second is how fast nerve signals go down nerve fibers. Doesn't compare too well with the robot or electronic systems, where the speed of electronic propagation is about half the speed of light. So you've got a factor which is about 1.5 million times. So the robot can work, its feedback path can work 1.5 million times faster than a human. So there's the robot, nothing like a human, of course, but what you notice is there are a lot more sensors on a robot. You can have radar, LiDAR, ultrasonic, infrared. You don't just have 5. I counted 50 or 60 that are useful for making androids or driverless cars. Then, of course, that goes into a computer. You have a lot of signal processing. You've got to plan paths. You've got to try and understand the environment. And software and hardware just really isn't up to that yet. The actuators, you've got a lot more than humans. You've got electric motors of various types, brushless motors, stepper motors, synchronous motors, and so forth. Solenoids, not used very often. And you've got pneumatics and hydraulics, and you've got this very, very fast feedback. So apart from the software and hardware in the computing aspect, the robot is superior to the human in every other respect. Interestingly, the TV cameras are now better than the human eye, which is rather incredible. So these are the sensors. I said 50, that's a lot more than 50, isn't it? So these are the sensors that you can go onto the internet and go to your robot supplier, and these you can just buy easily. Even from hobby robot suppliers will supply most of these. A lot more than the human 5. So I thought I'd show a little bit of video of the DARPA robotics channels. DARPA is the Defense Advanced Projects Agency in America, and they have created this robotics challenge. The idea is you make a robot that can get out of a car, arrive at a disaster area, go through the door, climb over some rubble, and open a valve. And people make robots to be able to do that.
Well, it didn't you may not have encountered unknowns also. I mean, the darker challenge, they were being asked to navigate, a course they
This is a lab. This is...
Not to detract from the issue.
Thank you.
Yeah, so the robot consists of a lab as well?
Yes, and hundreds of technicians. I did a little talk with Asimo, the Japanese robot, and we talked and we shook hands. The team of people behind, they had another 5 Asimos in case that was broken, and there were a team of about 10 people to make sure, and there were 2 huge lorries. Robotics is liable to proceed much faster. Boston Dynamics started out as a university department, people having a lot of fun, getting a bit of money from the American military. But now, people are very serious about putting very, very serious lump sums of money in. So Ford, General Motors, Mercedes, Benz, Volvo, Nissan are all pouring billions of dollars into trying to be the first to produce a driverless car. And people are talking about driverless cars on the road in 2020, which is fairly soon. You don't need to copy humans. So the good analogy of human vision is a TV camera, and you'd think the first thing you do if you're making a driverless car is put in a TV camera. No, they don't. There's no TV camera. It's done entirely by a 64 beam 3D LiDAR laser time of flight. So these things send out a pulse of light and measure the time it takes to come back, which at the speed of light is a very, very, very short length of time. It's amazing that sensors could even do this, let alone with 64 beams at once, creating a 3D picture of the scene. So where humans can recognize how far away they are from objects, we're interpreting using our brains, looking at the objects in front, and from the color and the size we can work out how far away we are. This produces a picture which is not based on light, it's not based on reflections or colors, it's simply based on range. So it sees entirely different way to the way humans see. We don't have to be like humans and have one sensor. You can have 4 radars if you want. Have as many as you like, they're not expensive. But they do cheat a bit in that they drive the car around first, the car makes its own map of its environment, and then they put it in and do the test. So it's not really, truthfully, properly driverless car. So if you want to make a behavior-based mobile robot, starting off as W. Gray Walter did, or some of my students do, the first thing you need to do is to be able to move forwards, backwards, and turn. And you want the machine to be able to do that by itself, to decide how fast to move, where to move, and so forth. It needs to be able to avoid collisions, not easy, with static and moving objects. You've tried to use that sonar, for example, and you find it's much more difficult than you realize. For example, if I was a robot and I wanted to produce a map of this room and I fired my sonar at that wall, the sonar would bounce off that wall, that wall, that wall, go away, and the robot would say there's nothing there and drive towards it. But if the robot is pointing at a corner, the sonar will go to that side, go across and come back, and the robot will get a very strong signal. And if I, as a robot, was fire at my ultrasonic at right angles to the wall, it would get a very strong signal. So the robot will say, oh, there are 4 strong signals for the 4 corners and the 4 walls, and it can't see the rest. So ultrasonic is not really what you need for a robot. It's quite difficult. It's got to be able to localize, and that's difficult. And it's got to be able to move efficient to a goal that you might give it. And to do that, it's got to plan a path. And you want it to be able to do that itself. You don't want to say, you have to go 1 meter, turn right, 1 meter, turn left, 1 meter, that sort of thing. You want the robot to be able to plan its own path. So this is a piece of research some of my students and I did, or just one student. This is a corridor at the university, and we wanted to make a self-steering mobile robot that would work off just one sensor, one TV camera. And the first thing you have to do, if you want to work like that, is to remove from the scene all this stuff that's irrelevant. You just want to catch the key features out of that and take out features which are not relevant to you. So you do a thing called edge detection, and what the computer does is it looks for pixels which have got a different pixel next to them. So if there are two pixels that are very similar, that's not an edge. And that's the picture it gets. So this is what the robot sees, just a lot of pixels at where there were edges. So what we decided to do was count up the number of pixels, and instead of looking at the scene as XY coordinates, to look at the scene as polar coordinates, because we're looking to measure angles. So we find that there are a lot of pixels, edge-detected pixels, at particular angles. So the robot has now decided that there are 4 strong angles there, and it can then extrapolate those, find what we're looking for, which is the vanishing point. So that's the point that the robot has to drive towards. So you've now given it a way of finding its path. And this, of course, is totally different to the way a human might do it, but it's a quick and easy way for a robot to do it, to find the vanishing point. It drives straight towards the crosshairs, as it were. So that's difficult. Computer vision is difficult. And what a chap called Hans Moravec has done at Carnegie Mellon University is look at how much computing power you need to do vision, how much of the human brain is dedicated to vision, and done a sort of comparison and said, right up there at the right-hand bit is where the power of computing reaches the power of the human brain. A little bit of an abstract idea, but something everybody's interested in. So the data points there, all the blue squares, are real robots. These are real data points. So this is the year 1900, where we're looking at electromechanical, 1940, where we're looking at solid-state relays, 1950, vacuum tube, like Gray Walter's machine, then the transistors in 65, and then along here we get integrated circuits, and he reckons the human brain is reached by about 2025. This actually is a graph produced by Ray Kurzweil, not Hans Moravec, but they agree. Or maybe one's using their one's data, I'm not sure. So we like to think of humans as being really rather special, but actually we're not. We have a genetic overlap with our siblings of about 99.95%, other humans 99.9%, chimpanzees 98%, cows. It's slightly worrying that we have 90% similar genetic structure to cows. It's very embarrassing, isn't it? Mice, well, quite a good genetic commonality, which is why, of course, medical researchers are able to use mice as examples of how drugs might work in humans. Even more worrying is when you get down to yeasts and E. coli. We have the same language, the same alphabet, the same genetically coded system as yeasts and organisms and bacteria. Similarly, we have only 3,000 different DNA base parts, rather a small, simple number, the same as the mouse. Not many different to the tomato, fruit flies, yeast, E. coli, and viruses. So the genetic complexity is a good bit more. So as evolution progresses, we've got more complex, but we're still the same stuff. There's a lot of stuff in this slide. So on this axis is plotted the number of types of cells there are in a particular organism. So in humans, we have hair cells, skin cells, brain cells, liver cells. We have 250 types of cell, which is up there. Bacteria only have one. You can estimate the complexity of what's in those cells by measuring, and I'm amazed they can do this, the number of grams of DNA there is in a cell. Very, very tiny numbers, of course, 10 to the minus 16. So the bacterium, the beginning of life in the universe, relatively small number of cells, relatively little DNA per cell, relatively low complexity. As evolution has progressed, we've got to humans where the numbers, same procedure, same trend, same language, just time difference. So, and the ratio of complexity between there, the bacteria, and us, I think from memory is 1,000 to 1. Or was it 10,000 to 1? But the ratio here is 250 to 1. So you could make a sort of fag packet estimate that human beings are 250,000 times as complex as bacteria. Same stuff, but not quite as different as perhaps we would like. So if you were thought of bacteria sort of wandering around in a sort of pool of mud, acting like sort of mindless robots, you could say we're descended from mindless robots. So comparing humans with robots, again, I should say what this phrase here, VUCA, is. It's a phrase that comes from American military, which is volatile, uncertain, complex, and ambiguous, which pretty much defines humans. And the American military are interested because that's how they define the battle space if they're working in an area of total chaos almost. The communications we're capable of, if I'm talking, it's about 4 kilobits a second. That's the data rate of people talking. Computation, we just don't know very much about the brain yet. For the purpose of robots, we have 2 senses which are useful, vision and sound. Touch, taste and smell are not particularly useful. And we just have 1 actuator, muscles. If you want to make a robot like the DARPA ones or the Boston Dynamics humanoids, the control theory is very, very advanced. The mathematics of control theory is probably complete as far as robotics is concerned. I'm standing out on a bit on that. Communications, we're very, very good at that. We're happy sending, or at least not us, but technology is happy sending data at 100 gigabits, 100,000 million bits of information a second. Very, very much faster than humans. Computation's still not good, but the sensors we've got for an Android, maybe 50, and actuators, again, motors, hydraulics, pneumatics, solenoids. The controller theory for driverless cars is solved, very, very simple, and it's easy to control a car. You just need a stepper motor for the steering and a pressure pump for the hydraulic brakes, and cars have got automatic gearboxes now, which are very good, and can change gear faster than a human can. I think my car claims to be able to change gear in 1/10 of a second. But then it is a Nissan GTR, which has a top speed of 197 miles an hour. I shouldn't be allowed to drive it. So driverless cars, everything is solved except the computing. So, in summary, human evolution, people argue, Stephen Jay Gould, for example, that human evolution has stopped because we have no natural predators, we don't have to worry about food in advanced countries, water or predators. Some biologists argue that that's not quite right, but at least it's painfully slow. Biological tissue is limited. You can't have wheels in biology. Biology, it's impossible for biology to produce wheels, and wheels are very efficient. And of course, nerve cells are very slow and so on. We're held back by reptile brain baggage. I mean the sort of thing of wars and people killing one another and jealousy and organizations where the boss tries to hold everybody down to make himself look better, that sort of problem. I guess we've all come across that, particularly if you work in university. Sensors, actuators, robot speeds, all much better than humans in robots. And these powerful technologies are being developed at speed, partly for military uses because they're very, very keen on being able to decode messages and of other people, and prevent our own messages being decoded. So ministries of defense around the world are putting a lot of money into quantum computing, DNA computing, optical computing, and so on. But AI and image understanding are real, serious, difficult problems. So here's the future as seen by science fiction. From Star Trek, there's Data, a humanoid robot made by humans. So that's what everybody is aiming for, the intelligent robot. And that's the prediction of science fiction, which are all saying we're going to be taken over and destroyed by robots. The saddest thing I find about some of these predictions are that in 100 years, when this is supposed to be taking place, they still haven't found a cure for baldness. Thank you very much. Any questions?